Hello, my name is Marc-Antoine, and I'll be presenting Large Self-Supervised Model Bridge the Gap in Domain Adaptive Object Detection. This work was done in collaboration with Anas Mahmoud and Professor Stephen Waslander at the Trail Lab. The task we're trying to solve is domain adaptation, specifically for object detection. The main motivation for this task is the high cost of labeling datasets. The idea is that we want to use existing source datasets with a large number of labels and transfer that performance to other datasets instead of having to generate new labels on these datasets. Common use cases involve adapting to adverse weather, in this case something like foggy cityscapes, adapting to a new operating setting, something like BDD, or some mix of both, something like the ACDC dataset that has both different settings and adverse weather. Before presenting our method, I'll first summarize some of the existing strategies. In the simplest case, we use source-only training and also evaluate on the target domain. To actually do domain adaptation, the earliest methods considered aligning the representations from the source and the target domains at the image level. This is done by minimizing some distance measure between the domains. A next set of methods considers a self-labeling approach. Starting from a model training on source-only data, we can instantiate a copy of the model, the teacher in this case, that is an exponential moving average of the student. This is often referred as the mean teacher approach. By sending the same image to both the teacher and the student, the teacher generates box proposals that are filtered by confidence thresholding, and we can use those filtered boxes as pseudo-labels for the student. While only easy examples are initially kept, as the student and the teacher become better trained on the target domain, more and more labels are generated. Many recent methods combine both approaches, using both domain alignment and pseudo-labels. Of note, the use of pseudo-labels allows the alignment to be done at the instance level, increasing specificity. However, we find that these methods are lacking. First, we find that domain invariance at both the image and instance level is flawed. On images, the background and common classes can dominate the loss, while at the instance level, the quality of the alignment is sensitive to the available target domain pseudo-labels. Note that in many driving scenes, the actual objects of interest may represent a small fraction of the image, and common classes will be overrepresented. Next, we have issues with the mean teacher approach, particularly because it assumes that a model trained on source-only data can generate pseudo-labels of adequate quality, and it is possible to bootstrap the performance from easy to hard examples in the target domain. In practice, however, we see that this is not always the case. And in some cases, the poor quality of the pseudo-labels leads to training issues, even complete divergence of the proposals. To highlight issues related to mean teacher, we compare validation performance when transferring to different target datasets. When going from cityscapes to foggy cityscapes, the domain gap is small and pseudo-label generation is stable, leading to improvements on the target domain. This is not the case when transferring to BDD. We see that training is much noisier and becomes sensitive to errors in the generated labels. To solve both of these issues, we propose to leverage vision foundational models. For domain invariance, we find that models such as Dino v2 have features that generalize well across domains. We propose to align the student model's features with those of the Dino encoder, learning features that should be transferred better to the target domain. For pseudo-labeling, we similarly leverage the strong generalizable features of VFMs by training an object detection head on top of a frozen VFM features. While the detector is trained only on source data, this model can be a better labeler compared to mean teacher, and because it is trained only on frozen features, it allows us to transfer to multiple different unseen target domains. Our proposed method is composed of three main steps: training the labeler, generating target domain labels, and training the final student model. First, the labeler is built from a frozen VFM encoder and an object detection head. Only the object detection head is trained, and we only use source data. Next, we generate proposal for the entire target domain training dataset in a single forward pass. Similar to mean teacher, we threshold on class confidence scores to select proposals that are of a high enough confidence to be used as pseudo-labels. We use this fixed set of pseudo-labels in the next step. Finally, we train the student model. We use the generated target domain pseudo-labels as supervision for the detection loss on the target domain. In addition to this, we add an alignment loss between the patch level features of the student backbone and those generated by a VFM model. This is evaluated individually for each image from both the source and the target domain. We'll now go into more details on the patch level alignment. Here, we use a simple alignment loss for the student to the VFM. We simply minimize the cosine distance between the patch features of the VFM encoder and those of the students, which are first interpolated to the required size and transformed through the true two-layer projection MLP. In practice, we see that using this alignment leads to a representation that has better class separation, which improves performance. Finally, we present some key results. On BDD, we obtain state-of-the-art performance by a very large margin, particularly on rare classes such as trucks, buses, and motorcycles. We also obtain state-of-the-art performance on foggy cityscapes, even if the domain gap is small. Foggy cityscapes uses the same labels as cityscapes, and so mean teacher approaches should generate accurate pseudo-labels, but our labeler still performs better. We also highlight that our method performs better on all test splits of the ACDC when compared to a mean teacher baseline. In ablations, we find that performance of the student scales with the size of the frozen VFM encoder used in both the labeler and the patch level alignment. We also find that our performance improvements are maintained when increasing the size of the student model. Thank you for listening. We provide links to both the paper and an implementation of our code in these QR codes.